Oh, thank you for the invitation. I'm very happy to come back here and give a talk. So today I'm going to talk about the Boltzmann equation without angular cutoff. Let's just get started. So I show you a picture of Boltzmann and Maxwell. I like to do this in the beginning of my talk on this subject. This is Boltzmann on the left, and this is Maxwell on the right.
Who's the guy that's in it?
What? Maxwell. Maxwell.
Yes.
I found these pictures on the internet. And so the overall theme that if you remember only one thing from my talk, I want you to remember this theme that the full Boltzmann equation, which I'll tell you about in a moment, is a physical non-local geometric fractionally diffusive somewhat degenerate partial differential equation. And I like to tell people that these are words that you don't associate with these guys really using in the vocabulary that much, in spite of the fact that they derive the equation. And so I like to mention a little bit of the history that I know about this talk, about these guys and about this equation when I give this talk, but usually I don't think that my audience knows more history of these equations than I do, but I'm not sure if that's the case today. So I'll try to be careful. Okay, so here is some of the modeling assumptions. The Boltzmann equation was derived by Boltzmann in 1872 and Maxwell in 1866, and it models the behavior of a dilute gas. So you have approximately 10 to the 23rd particles. They obey the laws of Newtonian mechanics. Was there a comment?
Maxwell did just a special case of the velocity distribution of the
Oh, I'll talk about that later on a little bit. Maxwell. So what people normally say is that Maxwell derived the equation and Boltzmann proved the H theorem, and so people call it the Boltzmann equation because he really gave the quote-unquote proof of the H theorem. And Maxwell. Yeah. Yes.
He wrote it down in modern weak form.
Yes.
And what he did was he made an over-specific specification of the force law. He sort of did 1 over R6 force
Yeah.
law, the collision kernel doesn't
Yeah.
depend on relative velocity.
Yes, yes.
Max.
That was a simplification he introduced and claimed to have experimental evidence for.
This is what we can now call the Maxwell molecules case. I'll mention a little bit more of that later on.
How much was Boltzmann aware of that or not aware?
He was fully aware of it. He cited Maxwell's work, and he was building on what Maxwell had already done. I understand in the UK some people call it the Maxwell-Boltzmann equation, but most of the time in the literature people just call it the Boltzmann equation. And Maxwell went on to study electricity and magnetism, so it wasn't like he just stopped working and doing productive things. Okay, so each particle has its own position and velocity, travels in a straight line until it collides with another particle. We only allow binary collisions. You can make an argument that's somewhat rigorous that higher order collisions don't really happen that much. Collisions obey the physical conservation laws of momentum and energy. And the Boltzmann equation is derived by taking a certain continuum limit that you call a Boltzmann grad limit, where you send the number of particles to infinity and you send the size of each particle to 0. And the Boltzmann equation is probabilistic. It describes the evolution in time for an arbitrary particle in an ensemble of particles with a given initial position and momentum.
But isn't that probabilistic?
Well, it's a you can interpret it as a probability if you like, or I'm a PDE person, so I think of this in terms of PDE. You have a conservation of mass, and you can think of it as some sort of an average. Yes.
Yeah, but I think it's an equation with empirical distribution.
Yes, you can call it an empirical. I'm sorry, I'm going to have to. I forgot to set my computer to not go to sleep frequently, and now it's thinking a lot. Yeah, so I normally so you can call it an empirical distribution, and that's more reasonable than saying it's probabilistic. Probably.
Yeah, I think in Lamford's long
Yeah.
article was very clear.
Yes. Here, I know how to do this very fast. Oh, you are doing it. No, 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 no. During this playoff, after never good view. Oh, we're in the wrong place. Oh, you're using preview. Full screen. Okay. Oh, you have to unplug that. That was the issue. Yeah, so yeah, so sometimes I like to mention a little bit of history, but I will. So this is the picture. I will only mention some of it in the interest of time, and because a lot of you probably know at least as much of it as I do. So I took this picture off Wikipedia. It's not really indicative of anything, except you see particles moving around in a box. And this is the picture. Okay, so here's the Boltzmann equation. You have dTf plus v dot grad xf equals qff, and x is in some domain, v is in R3, and t moves forward. And you can think of f as a probability density, or maybe better, an empirical distribution. And omega is a domain, and you have free transport, and q is a collision operator. And this was derived by Boltzmann and Maxwell from rarefied gas dynamics, as we've been saying. So here's the conservation laws. So given two particles with velocities v and v star, after a binary collision, they have outgoing velocities v prime and v prime star, and these you can assume the modeling assumptions that these particles obey the conservation of momentum and energy. So you have v plus v stars, you could have v prime plus v prime star, and the squares, the sum of the squares is also equal. This gives you 4 equations, but you have 6 unknowns because each of these quantities are in R3. And so since there are 6 unknowns and 4 equations, the set of solutions can be parameterized by the sphere, and there are several parameterizations of these so-called post-collisional velocities. This is one of them. And so you have a 2-parameter family of solutions to this problem. And this describes, you can interpret this as describing the aftermath of a binary collision probabilistically. Yes? Yes. Oh, I'm sorry. I thought I was using a microphone, so I wasn't. Oh, this is just recording. Okay, so I didn't want to speak too loud because I thought that would overwhelm you, because I assumed I was on a microphone, but I'll try to speak louder. Sorry about that. Okay, so sure. So the Boltzmann equation, again, you see it up there from 1872. And the next thing to discuss is the collision operator. This is the main quantity that we study. Excuse me, I'm getting over a cold. So you can think of Q as a function of both f and g. It's a local operator in t and x. And it's an integral over dv star, and an integral over d, what we call d sigma, which is the integral over all the angles. And then you have what I call a collision kernel, b of v minus b star sigma. And you have this difference of the functions, f prime star g prime minus f star g. And g is a function of v, f is a function of v star, g prime is a function of g of v prime, and f prime star is a function of f of v prime star. So these are all functions of different variables in the velocity components. Oh yes, they're, I just described them on the last slide. So you have a v star, a v prime, and a v prime star. And the v's and the v stars are pre-collision, and the v primes and the v prime stars are the velocities post-collision. And So you have this difference. Okay, and it's already been mentioned, but I'd like to mention the Lamford result, which rigorously derives the Boltzmann equation for hard spheres from classical Newtonian mechanics on a very, very, very short time interval. And this is, I like to think of it as a highlight of the field of deriving partial differential equations from classical mechanics. And you have subsequent results by other people, in particular Illner and Pulverenti and other people about, okay, yes? Oh, sorry. In particular, Illner and Pulverenti about deriving the Boltzmann equation for initial data near zero globally in time. This is a huge field. I can't really describe it in any detail, but but you can derive the equation in some sense. In some situations, you cannot derive the equation. There's no known fully rigorous proof that I'm aware of a derivation of the non-cutoff Boltzmann equation, which is the one I'm going to be talking about results about today. There are big problems in that area. Okay, so oh, what happened? Oh yeah, so the aftermath of the let me skip this because everyone here knows this. Okay, so the Boltzmann equation. So the aftermath of a binary collision can be put into roughly three categories: hard spheres, inverse parallel interactions, and the Coulomb potential case 5r equals r to the minus 1. And I think that most of you are very familiar with these different derivations, so I won't spend too much time discussing all the words on this slide. So the
I think your assumption may not be right, but
oh,
the conclusion is not
okay. Well, as long as the conclusion is okay, then I'll continue. So Maxwell, in his big 1866 treatise to the Royal Society, computed this collision kernel B from the potential, from the inverse parallel potential 5r equals r to the minus b plus 1. And this is now taught in many first-year graduate or advanced undergraduate statistical physics textbooks, and it's basically his derivation. He showed that the kernel B takes product form in its arguments. So you can say B is equal to V minus V star to the gamma times lowercase b of cosine theta, where cosine theta is this scattering angle, V minus V star unit vector dotted with sigma, and sigma is what you're integrating over. The problem with this, do you have a question? Yes?
So, when do you want to apply Boltzmann and when do you want to apply Blasov? Blasov is nice too, isn't it?
Yes, you want to apply Boltzmann in situations where you expect to have collisions, and you want to apply Blasov in situations where you can neglect collisions. Yes. Well, yeah, so in some sense, there's an interesting argument that's never really been made totally rigorous in the Landau-Lifshitz books. That was, it may also be in Sponge book, I'm not sure. But it, but, yeah, but you can use complex analysis to derive collisional models like the Belescu-Lenard model and maybe also the Landau model from the Vlasov equation, from Vlasov-Poisson, some high order Vlasov-Poisson model. And there's a highly non-rigorous derivation of this in several physics books. The one that I'm most familiar with is Landau-Lifshitz. So there are connections, and there collisional kinetic models like the Belescu-Lenard. And maybe since you can derive Landau from Belescu-Lenard, you can derive Landau, but that's not something That's even less rigorous. There's only really one math paper on Boltzmann that I'm aware of, and I wrote it. So there are connections, but the basic question, my answer to when you want to use the Boltzmann equation is in situations where you want to model collisional effects. And people normally think of Vlasov as a collisionless model, although it does have some collisional effects, as was discussed. Okay, so there's this angular singularity here. Sine of theta, b of cosine of theta, is of the order of theta to the -1 to the -2s, where s depends on p, and theta can be taken to be between 0 and pi/2. There is a reason why I'm not telling you what b is. It's because b is not computable in terms of elementary functions. That's something you can prove. There is an implicit formula for b that is one of those implicit formulas that tells you that you have a unique solution to this lowercase b, and this implicit formula can tell you the behavior of this b, this lowercase b, but this implicit formula cannot give you a closed form solution to this lowercase b, except in one specific case, and that's the case when p equals 2, and in that situation you have the well-known Rutherford cross-section that you could derive. Okay. Also, this kinetic factor v minus v star can be singular to the power gamma. Gamma can be as singular as -3. So you have this cross-section, and it can have singularities in both the relative velocity v minus v star and in the angular singularity. So this is the full Boltzmann equation that was studied by, that was written down by Boltzmann and Maxwell. And so you can, from a historical point of view, I like to make this point that this looks from an 1860, 1870 point of view like it's just equal to infinity, possibly. And you can ask the question, why didn't these physicists, Boltzmann and Maxwell, throw out this equation and look for a better equation that wasn't equal to infinity when they had a lot of this information available to them? And the answer is Maxwell did something quite amazing, in my opinion, for a physicist in 1866. He, as Eric already mentioned, he wrote down the Boltzmann equation in weak form. So here's an example of a physicist in the 1860s writing down a weak solution to a partial differential equation in some sense. And of course he didn't write this, and he didn't use this notation, but I don't feel like telling you about his notation right now. So Maxwell made sense of this equation by looking at it in some weak form and saying that there was sufficient cancellation to make sense of the equation. Okay, so that was the situation. And there wasn't an enormous amount of progress on the Boltzmann equation. There was some, and I'll tell you about it later on, until after the 60s, let's say. And there was, at that point, there was an assumption that was made. And the assumption was you could either make the assumption B is in L infinity or B is in L1 on the sphere. And both of these assumptions are dramatically violated by the physical model that we were talking about a minute ago. I'm overgeneralizing, but I'm also making a true statement that the vast majority of research on the Boltzmann equation from the 1960s to approximately the year 2000 made these assumptions. And there were a lot of papers in this time period. And I still get asked to referee a lot of papers today that make assumptions like these because even after we understand the singularity better. Yes?
If you take a finite range potential, I mean, then these assumptions are actually satisfied. I mean, the one which is right on top of your hard sphere.
Yeah.
Yes, but any finite range potential.
Yeah, well, that's right.
Then that's okay.
I'm not saying this is the worst assumption in the world. I'm saying that it was made for a long time. There certainly are situations where you can also derive the Landau equation formally from finite range potential.
Or you could plug in a quantum mechanical cross-section, then the total cross-section will be finite. I mean, you're sort of fighting with the fact that in classical mechanics, total cross-section diverges for potentials that go to the finite range, right?
Well, there's also quantum analogs. I mean, in the following sense, if you look at the relativistic Boltzmann equation, so you incorporate special relativity into your model, then the issue of deriving the equation is much worse, because as far as I know, there are no even underlying dynamics in the relativistic case. But on top of that, there's no body of cross sections that you would want to derive. There are a few in the physics literature, and they're derived using quantum mechanics and Feynman diagrams and things like that. And they have infinite range potentials in that situation too. So they have infinite range cross sections. No, they have there's an analog of the Rutherford cross section, and there are cross sections with angular singularities. There are cross sections with angular singularities in that. This is not just a problem with Newtonian mechanics, as far as I know. I mean, I'd be happy to discuss it with you further. I admit that I'm not the biggest expert in the room on this topic, but I am aware of cross sections from quantum mechanics that give rise to angular singularities. Okay, but the point that I'm making is that not that there aren't other models that people can study legitimately that give rise to cutoff cross sections, and not that that's not a legitimate thing to study. The point that I'm making is that what appeared to be going on in the literature is people started from this cross section, took this kernel, and cut off the angular singularity, and that was what happened, and that was the way the assumption developed. And so I want to make the point that this gives rise to a different model. So if you make these types of assumptions, then, for example, cutoff versions of the Boltzmann equation propagate singularities, and there are results such as Boudin-de-Villet, Tuan-Li Yang, and Berny-de-Villet. And on the other hand, the full Boltzmann equation without cutoff experiences smoothing effects. And these kinds of results go back to Pierre-Louis Lyons, de Villet, and more recently Chen de Villet he, and this team of 5 people, Alexandra Morimoto, Ukai, Yu, and Zhang, who I call AMUXY, have written a lot of papers on smoothing effects for the equation. So there is a big difference in the behavior of these two models. And also what we can prove with Grassman is that the Boltzmann equation without cutoff experiences faster convergence to equilibrium.
When you speak of that, you always think that you start with a long-range potential and then cut off.
Yes.
If you start with a short-range potential, then you always have automatic cutoff.
No, well, there are arguments that you can derive the Landau equation from a short-range potential, which is not cut off.
I was wondering about your statement. The full Boltzmann equation.
Oh, so this one.
No.
That's what I mean by full Boltzmann equation.
Which has specifically the 1 over r potential.
Yes, so the 1 over r potential, absolutely. I should be more specific. That's a good point.
Is there a corresponding statement or not? Your middle statement, if you start with short-range potentials, does the Boltzmann equation propagate singularities, or does it no singularity propagate?
Well, you would have to look at the kernel and you would have to study it. But if you have assumptions like these on your kernel, then yeah, you would propagate singularities. These are specific theorems with a series of assumptions that I'm not stating because of time constraints. And you might look at these specific theorems and say, I don't know if I can verify all the assumptions. But this is philosophically my point of view and the point of view of several people who have worked in this area, that there is this difference in behavior. But if you have a specific model,
Like heart spheres.
yeah, the heart spheres. This would happen. Heart spheres.
Heart spheres.
Heart spheres. It would happen. This would happen. Yeah, absolutely.
The statement is that the smoothing effect is a contribution of the non-linear term and not of the kinetic term.
The smoothing effect is a contribution of the angular singularity in the nonlinear term. Yes, that's absolutely the statement. The smoothing effect is a contribution of this singularity. I will explain this more right now. Okay, so the Boltzmann collision operator without cutoff has been widely conjectured to behave in this way. So if you think of G as a parameter function, and you think as F as the mapping into QGF, where F is really the second component of this Q, then there's a conjecture that is developed, it's now proven, but that this operator is of the order minus Laplacian in the V variable to the power S of F plus lower order terms. And the linear intuition is due to Carlo Ciorcignani in his 1969 book. What he did was he calculated the eigenfunctions of the Maxwell molecule case, and it was clear that the eigenvalues of the eigenfunctions behaved like the fourth power of the Laplacian. So this conjecture is correct to the power S, but it does not take into account the so-called collisional geometry of the model. This is an isotropic flat Laplacian, and so what we can prove is that the situation is a bit more complicated in that the mapping F into G of F is correctly some Laplacian to the power S, where S is the S from the previous slides. It's a fractional power, but this is a metric Laplacian on the paraboloid in R4 projected down to R3, and you also have to multiply by a power V to the gamma plus 2s, where V is this normal bracket V. So if R3 is identified with the paraboloid in R4 by means of the mapping V into V, 1/2 V squared, then Laplace V is the metric Laplacian on the paraboloid induced by the Euclidean metric on R4. G is a parameter, a function. Yeah, we think this is, I'm trying to explain intuition, and I just use G as a parameter. So G is something that would not be diffused on. It would just appear outside of the diffusion. Okay, and by lower order terms, I mean terms that do not differentiate. So I show you this picture. Erica has seen this picture before, if he remembers, but other people probably haven't. So if you try to do normal, so I try to distinguish the difference between these two Laplacians. If you try to approximate heat diffusion with a fractional S power Laplacian, and you take a bump and you set it in the middle of a circle, which is what we did here, then the bump would spread out evenly in all directions. But if you take the Laplacian to the power S and you hit a bump in the middle, then it doesn't, excuse me, I'm still getting over a cold. The bump doesn't diffuse evenly in all directions. It pushes in different directions with different strengths, and those directions change and the strengths change, and this is a static picture, but the picture would really be dynamic and it would be moving all over the place. So it's not just even spreading. Okay, so let me precise what we actually do. So this sharp geometric fractional diffusive behavior is in this space that we call NS gamma. So this is the behavior. The Boltzmann equation experiences diffusion like this quantity right here, and this is sharp. So if you consider a fractional order Sobolev space with no weights, then you think of D as the Euclidean metric on R3, then this is a fractional Sobolev space of order S. But we have a weight here. We have this V to the gamma plus 2S. There's a 1 there for technical reasons that I prefer not to describe. And there's a metric that includes this V squared minus V prime squared term that I don't want to explain in too much detail, except I want to point out to you that it's not higher order. It's in fact an essential part of the sharp diffusion of the Boltzmann equation. And so we can make a precise statement. So Q of GFF in the L2 coupling behaves with upper and lower bounds like F to this NS gamma norm plus this weighted norm plus terms that don't matter. And you can do this, and now I precise the question about what G is. So you can do this thinking of the function G as a parameter that appears in the constants, and you can do this assuming only that G is in L log L intersect L1 on a ball of radius R of center 0. No, we found it. This norm wasn't conjectured at all. We found it. So we discovered the sharp diffusive behavior of the equation, and the conjecture was this, and this is correct locally, but it's incorrect globally in the velocity variables. And to prove the kind of results that we are interested in, you need the correct sharp global behavior. And we figured out what it was, and that was a very important part of our proof. Okay, so I explained to you where the intuition for this norm comes from, rather than explaining the proof. Okay, so to flatten the diffusive effects of the collision operator, I define a non-relativistic mass shell. So if you're familiar with a mass shell in special relativity, I want to define a non-relativistic mass shell, which is an artificial construction of my own as far as I know. But if you consider something like V underbar, which is 4 variables in R4, and you define the 4th variable to just be the square, then you can lift R3 into R4 as long as you multiply by a delta function. And then you can do this on all the variables. You can do this on the V prime variable, the V star variable, and the V prime star variable. And you put a 4 delta function in there which encodes the conservation laws, and you put a delta function in there for each of these variables, V prime, V star, and V prime star, which encodes the conservation of energy. So this 4 delta function encodes the conservation of mass and the conservation of energy, the conservation of momentum and the conservation of energy. And then you can re-express the Boltzmann equation in this way. This is something that's done a lot in relativity. Now it's hard to find this done in non-relative Newtonian mechanics, but you can do it. And when you look at the Boltzmann equation in this way, the angular singularity in the collision kernel occurs not only in V prime going to V, but also in V prime squared going to V squared. And so this is where my intuition for this behavior comes from. So I want to explain it to you because we decided against putting it in print for some reason. But nonetheless, this is my intuition. Okay, so I can, since this is quite technical, I'll show you a picture that my collaborator Phil Grassman made a while ago. So if you try to if you try to do some kind of Fourier decomposition of the this angular singularity that I'm telling you about, and you do it in the flat normal standard way, what you get is a big mess, and the reason is because the wavelengths change, and when you take everything apart, you don't know how to put it back together again. And the reason for that is because the diffusion is not isotropic. This is a parabola, and this is flat space. This is some kind of a naive picture of a wave. Yes, this is a spring. This is the. Yes. I'm saying that if you look at this frequency, the wavelengths are not uniform, and if you stretch this frequency onto the parabola, then the wavelengths are uniform. So if you do a decomposition on the parabola, then you get uniformity, and you can prove estimates using some kind of frequency decomposition. If you do a flat frequency decomposition, then you get ugly non-uniformity, and you have no clue how to prove estimates.
What you're saying is that the spring on the right is a cartoon of the high frequency ion.
Yes. Yes, that's correct. Yes, this is the correct geometry in which to view them. That's my explanation. Okay, so this is better than showing you formulas, although I might try to show you formulas later on. Oh, I've gone quite slow. So I wasn't sure which information you would find interesting, so I prepared more slides than I could present. You might see me zoom through them at the end of the talk, but I might fast forward to the end. Okay, so you have the conservation of mass, momentum, and energy, which hold formally for a solution, and then you have equilibrium states, which are these Maxwellians. So Maxwell got the Maxwell. These, if you work in a different field, you might call these Gaussians, but in this area, Maxwell got them named after him because he rightly wrote them down. And so we didn't get the total shaft in the derivation, in the namology of this equation. And there's a 5-parameter family of steady states. The density is rho, the bulk velocity is u, and the temperature is T. And these are you might recognize these as the fluid variables. And there's 5 conservation laws. And so the 5 conservation laws of the 5-parameter Maxwellian predict a unique equilibrium state given each initial condition. And you also have this 140-year-old Boltzmann H theorem for solutions, which I put the correct minus sign in front of it, and then you get that entropy is increasing, and this is related to the second law of thermodynamics. And the entropy are maximized by the Maxwellian equilibria, and Boltzmann himself predicted convergence in large time to these equilibria for solutions to the Boltzmann equation, and the quote-unquote proof, which you can find in a lot of physics textbook, is mathematicians like to say is held back by quote-unquote slight analytical difficulties, because you don't know whether or not the solution to the equation satisfies the properties that you're using when you write down the proof. This is a big open problem for mathematicians to prove. There are the big result of Villani and de Villette got mentioned in the Fields of Matter Lauderdale last time of Yao about proving convergence to equilibrium for large data solutions, modulo making very high order assumptions on the solution that you still don't know whether or not they exist. There's now a literature in this field that I won't discuss because I don't have time, but what we do have is a rigorous proof without making any unverified assumptions in the close to equilibrium context, and that's our result. Okay, so before I mention our result, I'll mention a short incomplete list of old results. So Hilbert worked on this in the 1900s, and Ukai and Ellis-Pinsky and Illner-Shinbrat, Kaflish, Ukai-Asano, Deparnell-Lyons, Guo, and many other people. The S's indicate myself, and sometimes I explain all of these results, but I think that I don't have time today, so I'll just show them to you, and happy to discuss them with you later if you want. Okay, so this is what we do. We linearize the Boltzmann equation around a Maxwellian, and we choose a specific linearization, mu plus the square root of mu lowercase f, where mu is the normalized Maxwellian. Okay, so you have phi of r is equal to r to the minus p minus 1 for p greater or equal to 2. P equal 2 implies lambda. P strictly greater than 2, strictly less than infinity implies Boltzmann. So when P equals 2, you get 1 over R. And in that situation, you get the Rutherford cross-section. And Landau, in around 1936, argued that the Boltzmann equation was invalid for this collision kernel. And Villani wrote a one-page argument in his PhD thesis that Landau may have been somewhat aware of, but not rigorously aware of, that says that if you plug any smooth function into the Boltzmann equation for the Rutherford cross-section, the collision kernel is either 0 or infinity, so it doesn't make sense. And that's Landau argued that it didn't make sense. And he, in mathematical terms, he did a Taylor expansion and took the first order correction to the singularity and derived the Landau equation. And that is a different equation. It has its own set of results. What I am talking about is the Boltzmann equation for p strictly larger than 2. Guo has some results for the Landau equation. There's a literature for the Landau equation. David Villani, not this paper, but different papers, have some results for the spatially homogeneous Boltzmann equation. There's a yes, there's a whole literature on the Landau. Yes. 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 Short distance. Well, I mean, there are a list of situations that are described in, for example, Villani's review article on the Boltzmann equation, where he says that for p equal this number, there are 6 or 7 plasmas that you want to study, and for p equal this other number, there are 7 or 8 plasmas that you want to study. And I'm happy to have a discussion about whether or not this is a worthwhile model. I mean, I came at this really from a mathematician's point of view, not looking for a hard problem to solve, but looking to remove an assumption that had been made in the mathematical literature for several decades. And I the people, the mathematicians that I discussed this problem with would tell me that it was extremely physical. I'm sure that there are other people who might have a different opinion. That's the best answer I can give you at the moment. So yeah. But it is a model. It is a model cross section. It's not a. I mean, if you want to change the cross section, you get even more hideous and insanely ugly models that are even less well understood. And this is, in some sense, an example of. But this behavior does happen for other cross sections too. This is not some this behavior that I'm talking about in the angular singularity is not a peculiarity of this range of P's. I can say that I've seen it in other situations. Okay, my wife wants to tell me something. Sorry. So hopefully I can tell you my theorem. So the perturbation, the lowercase f, looks like this. Partial f partial t plus v dot grad xf plus L of f is equal to gamma of ff, where gamma is this formula and L is this formula. And they are all, I describe L in terms of gamma and gamma in terms of Q. So I have rigorously told you everything. Boltzmann's H theorem predicts that f converges to mu as t goes to infinity, which predicts that lowercase f converges to 0 as t goes to infinity. And this problem is hard because the linear operator has a large null space. You have this projection, which is 5-dimensional in velocity, but it's infinite dimensional when you include the t and the x variables, and it sends L to 0. And this is not an artifact of the linearization. There's a similar projection for the nonlinear problem. Okay, and now I normally like to tell people about my Sobel of spaces because I like to be honest. I'm not going to read these to you today. Sometimes people love this slide, other times people hate this slide. But some people think I'm being dishonest if I don't show this slide. Some people don't want to see this slide. So I'm not going to even read it. I'll just move on. So this is our theorem. I won't read it to you precisely.
What is your physical space? Oh my God. Are you on periodic or?
Yes. Okay. So we work in T3, where in physical space with periodic boundary conditions. We can also work in R3, and I have results in that direction too. The situation where you have physical boundary conditions is open, and it's interesting. The problem of studying boundary conditions for the Boltzmann equation is hard, and the only results that I know about are either conditional, or they assume that you don't have the angular singularity. So there are 0 results that I'm aware of that are unconditional for this model that I'm discussing for boundary conditions, other than periodic boundary conditions. Okay, so here are periodic boundary conditions. So
what do you do then with potential? Periodicize it, or what do you do? I mean, how do you define 1 over R? Something can be periodic box.
Well, you can do it in the whole. You have results in the whole space. You could It's just in the collision cross section. That's correct. You can periodize the box. You can work in the whole space. You can also work in the whole space. So I have theorems in the whole space, and this theorem is true in the whole space. You can, I mean, I'm not a derivations guy, so I am a PDE guy, and so you're asking me questions that I can try to discuss with you, but I don't know if I'm not an expert at that. And I believe you can periodize the potential, but or you can periodize the box, but I'm again not an expert on that, so don't take my word for all the details. But we proved this in the torus, that case, because that case was the one that was mathematically interesting to us for studying the equation. And you can also generalize this to the whole space, and I have done that. So that if you're, so you can do that. Okay, so the idea is you take some derivatives and you work in some Sobel space and you assume a smallness condition, and then you get a global solution. And in the case of these parameters that we call the hard potential case, the global solution decays exponentially fast to equilibrium. And in the case of the soft potentials, the global solution decays polynomially fast to equilibrium, and the polynomial decay rate can be made faster by assuming faster decay of the initial perturbation. And we have positivity. Oh, so we should discuss this with Eric. They have some results, they have some counterexamples to that. It might not be for exactly this model, but it's for very closely related models. And they have examples of very slowly decaying solution. Even in spatially, yeah, they have examples of very slow decaying. Okay, so I believe I have some old results with Guo where you can get decay rates like this. If you assume a lot more on the initial data, I haven't so far had the enthusiasm to try to work those out in this situation. I believe they're true in this situation. So you could probably get decay like this, but you have to assume a lot on the initial data, and so they don't violate Eric's examples with his collaborators.
I guess what's really striking with
Yes.
in the beginning, I mean, there's 2S, so what Bob is calling the
Yes.
between hard and soft is
Yes.
not what everyone before had called
Yes.
it. It's between hard and soft, which is only taking into account the gamma, because we cut it off, you don't see the effects of the S.
Yes.
Which gives you exponential decay.
Yes.
Larger rates, and you have expected to find it before.
Yes. So this is the point I was making earlier, and the point that Eric just correctly made, that people used to think that the barrier between these two regimes didn't include S, and it was just gamma bigger than 0, gamma less than 0. And so now we have a range of gamma positive for which you get gamma negative for which you get exponential decay, and that was surprising.
It's essentially P with the
Oh, so I go all the way back. Gamma is right here,
down at the bottom there is.
and gamma is right here.
This was Maxwell's mistake. He said E equal to 5. He said nature works that way because it likes symmetry and simplification.
Okay, so I fast forward slower than I want. Okay, so there are not that many results with a cutoff other than ours. There's this old paper of Alexandre Villani in CPAM 2002. So they have large data, renormalized weak solutions up to a defect measure. Some people call these Di-Pernoleons renormalized solutions, other people don't. But there's a defect measure here, mu, that's has a sign. It's not known how large it is. So you have to renormalize by this kind of a beta factor, and you have a weak solution. And this is what you can do for large data. There are recently new results that didn't make it onto my slide of Laura St. Raymond and Diego Arsenio. generalizing these types of results. They're very nice results.
You don't have a uniqueness, or
No, there's no uniqueness here. There's no. Whenever you talk about renormalized weak solutions for the Boltzmann equation, the uniqueness is gone. You can have there's an old result of Lyon's that he proved after Deperna had passed away that you have some kind of weak strong uniqueness. So assuming a very smooth solution to the Boltzmann equation, it's unique in the class of weak solutions, but you don't know if you have that type of solution. So you don't know uniqueness for these, that's right. And then you have this AMUXY team who wrote a theorem similar to ours around the same time, but they use very different methods. They use commutator estimates, and they used a completely different but equivalent norm. Their norm is very nice. It doesn't have this sharp geometric understanding of the diffusion that ours does. It's a rewriting of the Boltzmann equation where they use the exact kernel and they do expansions and commutator estimates. But they did similar. But so there's another result. Okay, so I mentioned that, and there are new papers. I mean, this field has been progressing in the last few years. I get asked to referee a lot of them. They're nice. There are a lot of new nice papers. I don't think I have time to talk about them too much, though. But they have to be. So, in a sense of bounded above and below by constant, there is only one norm. So, in order to prove these results, there is only one diffusion norm that you can use. And we have a proof that we've never published, because why bother, that these norms are actually equivalent. But whether or not you prove it, if you understand the methods, you know that there is only one norm, and you have to find it in order to prove these types of results. They look very different. I mean, this one. So this one is defined in terms of the collision operator. You have the collision kernel B, and you have G prime minus G, and you have the Maxwellian mu here, and then you have G squared times the square term, and so it encodes the same effects because the effects are all encoded in the collision kernel and in these integrals. But when you use this type of norm, you don't have to have a detailed mathematical understanding of the geometry, and they even admit that. I mean, they have said in their talks that that no one understands this norm, what it really means. But as I told you before in my description, there is a sharp geometric understanding of the behavior of the equation. I can prove it. I can take you to your office and prove it for you if you want to sit down for half an hour or so and listen to all my notation. But no, it's not. I didn't know if anyone cared enough to actually write down a proof of that. I mean, okay, so it's basically in our paper. So you could take our paper and understand it very deeply and generalize some of the techniques and prove the equivalence. Yeah, but okay. So so what else do I want to say? So I'm out of time. Let me skip all of this. So I wanted to. So I woke up one morning last year, and Phil Grassman sent me an email with a C-SPAN video in it, and I was amazed that he had gone to he was invited by the NSF to go to a panel where they give poster presentations to congressmen and their aides, mostly their aides. And Jerry McInerney got a math PhD from UC Davis, and he's now in the House of Representatives, and his aide saw, he may have actually met with Phil, I'm not 100% sure, his aide saw Phil, and he saw Phil, and he gave a, how do I get out of here? and he gave a 1-minute speech on C-SPAN. That was actually one of the one of the worthwhile things to listen to. There's no sound. So I don't get many opportunities to tell people about this, so I figure I should tell you. Hopefully this means I can get my NSF grant renewed next year.
I think it was favorable.
Yes, it was favorable. He was making an argument to Congress that they should give more money to the NSF because our result was NSF-funded research.
I'm sorry, was he favor or against?
He favor, yeah. Okay. Okay, so thank you. I don't want to